Okay, we're going to hand back exams in just a few minutes. I have a big stack of exam printouts. Hopefully Courtney will get here in a minute. I just want to make a special announcement. If you need to come by and you feel like, oh, I wonder if I'm going to pass this class, or, if you want to know what your grade status is, I can get it calculated up for you. I've already done it for a few people. And just stop by office hours tomorrow, and I'll be in my regular office. That's room PS 156 in the physics building over there past the student health center and the counseling center, and I guess that's Libra over there. So my office is over here on this side of the atrium. And just slide on over there, one door past the elevator, and I'll be in there. And we can do it privately, so you don't have to worry about everybody knowing your grade and stuff like that. And if you can't make it to office hours, you'll be able to look at your grade data and put it together sometime tomorrow, because I'm going to try to do a roundup of your clicking after today, so tonight or maybe tomorrow morning, and then post that. And once I post that, you'll be able to calculate your grade and so forth. And before we go to the exam printouts, I want to go over some of the clicking answers because they were kind of interesting. And get your clicker out, because I'm going to give you a clicker question in just a minute. And you're actually going to do what I spent most of the afternoon yesterday doing, and that's grade. You're going to grade a student's message. Now, here's the prefix, or the question. Why can you conclude logically that Procyon A has a higher surface temperature than our star, the sun? And I was intending for people to look at that diagram, the two spectra for the sun and for Procyon A. But a couple of you looked at other stuff, and that is fine with me. We're going to take a look at it. Now, how I do this, I decode each sentence from symbols into a readable sentence. All right, and then I read everybody's sentence. So in here I had 270 sentences to read. And then once I read it, then I give it a grade from 0 to 4. And I gave a lot of 4s yesterday, but there were some students that got a 0. And there were some students that got a 1, a 2, and a 3. Not too many, but that's partial credit. You won't be, unfortunately, you won't be able to break it out in the column, in the row of your grades page. You just have a number with this grade and then the grade for exam 2 smushed together. If you got a 7 out of 7, then you got 4 plus 3 full credit. But if you didn't get a 7, it's kind of, but I can tell you if you want. So it used to be that I could even upload your guys' sentences into the old web courses, but Canvas, they just are not with it. And it's either Canvas's way or the highway. So, but you have a grade for it. Now, full credit, as I mentioned, is 4 points. In the morning section, I forgot to change this, so this is what the morning section had. 87 students out of about 290 got 4. So that's getting close to a third, a little bit less than a third of that class. Of those sentences, 87 students, 70 of them were unique. In other words, there were 70 sentences, all of them I graded correct. And I want you to think about that for a second. A multiple choice test, you just have to make a decision, A, B, C, D, or E, and I have to make everything in that. But in this one, yay, Courtney's here. In this one, that's right, very appropriate. In this one, you guys write the correct answer. I have a correct answer in mind when I set up the answer key and stuff. But 70 people didn't, that came up with their own version, and I thought, yeah, that's good. That's a good reason. And we're going to go over some of them right now. So let's take a look at a few of these sentences. And you might just want to jot down some codes here. Here's the, the baseline diagram that I was thinking everybody would look for. And here's the question. Why can you conclude logically that Procyon A has a higher surface temperature than our star, the sun? Now, here's a code. You might want to jot it down. DAGP. So that's what I'm looking at. I have a big spreadsheet of data, and I take that apart into individual letters, and then I form a sentence. And the sentence for that would look like this. All right? Now, that's got all the little parentheses and stuff like that. So, and, little slash marks and stuff. So what I do is I read that and I grade it, but for you guys, since I'm just doing a few of these, I cleaned it up. Here's the cleaned up version. For that question, the student answered that the sun's spectral class compared to Procyon A's spectral class is dimmer than Procyon A's. Now that's a little redundant. Your English teacher might, put the chop on you for putting those last two words, than Procyon A's, or including Procyon A at the end. That's all right. I can read these sentences, for instance, I can read this. And that's just, that's the computer putting it together. And I can look at this, and I can think this. And then I decide, okay, 0, 1, 2, 3, or 4. This one got a 4. All right? Now you may be saying to yourself, Dr. B, what do the spectral classes have to do with that? The student wasn't looking at that diagram. That student was looking at the HR diagram. And my wonderful students, this is an example. Here's Procyon A and Alpha Centauri A. So it's pretty close to what the sun is. Those two are fairly close. So they're about the same neighborhood of the HR diagram. That student was looking here. And I love that because it tells me that the student is putting together two separate concepts, the surface brightness and the spectral class, that in matter of fact, I wasn't even thinking in those terms. But this is a good answer. And I said to myself, yeah, okay, that's good. Because, Procyon A is a little bit to the left. And it's a little bit up. That means it's spectral class F something. It looks like about an F5. All right, so all that is very righteous. And I love to see that. And that is the advantage of this kind of a question. You guys can catch me napping and force me to give you the money. So just like in that movie, show me the money. All right. You can tell me, Dr. B, show me the money. And you get it. It's because you're making me think. I looked at this and I thought, yeah, okay, good. All right. So yeah, that student got the money. All right, now here's another one. You can jot this one down. And this one's a long one. Boop. A lot of symbols. PRL, WY, DQL. Here it is. There's the decryption of that code. Procyon A's filter band. And here's what it looks spiffed up. So I read this in the spreadsheet, and I think this down here at the bottom. Procyon A's filter band V wavelength is larger than the sun's filter band B wavelength. All right, now this one's a 1, right? And you might think to yourself, Dr. B, they're talking about B filter and V filter. That's not bad. Because procyan A is going to be brighter in the B filter than the V filter, so it's not a bad. And many students mentioned that in their answer to number 1, and they got full 4 points, but not this one, because, there's no single wavelength in filter band V. And procyan, they maybe were thinking about, get my cursor over here, they were maybe thinking about the peak wavelength. That's what they should have said, but they said filter V wavelength. So this one's a little shaky. So I gave them a point, partial credit, because they were thinking B and V filters. All right? Now here's another one. And there's the other wavelength. It's a little shaky. All right, now here's another question. Answer. DHWTP. All right? Now, I don't know who sent this one in, but let's take a look at it. There's the decryption. The sun's color is R brighter than procyan A's. And so the sun's color is brighter than procyan A's. As a matter of fact, this is exactly wrong. There's no color, there's no wavelength band here of the SUN that's brighter, taller, that graphs up higher than procyan. The sun is all below procyan A. So this one's exactly wrong, 0. All right, question? Yeah, how do you know you got it wrong? Oh, so you're assuming that you got the calculation right, but you might not have.
But I checked the calculation and I got that.
Yeah, the calculation in this class was 6160. Is that what? Or 4823? 4823. Yeah, this one we had a red one. Yeah. So I could, if you want, you can come by and look, and we'll look at it and stuff. But yeah, the thing is, I'm reading all these things, and I try to read them carefully, and I make a judgment call. And like this one, it's just no dineros. The previous one, I did give them 1 point. All right, so, all right. Now, I want you guys to make a decision. This time, you make the call. All right, so on exam day, you write the answer. Hopefully it's a good one. Today, you're going to grade it too. I'm going to give you 1, and I'm going to grade it. Go ahead and set that. We'll start to get your clicker out. Let's do a question together. Yeah, it's a short answer. Here we go. Here's your sentence. PJWYD, procyan A's peak is R larger than the sun's. Oops, I forgot a quotation mark in there. And here's the cleaned up version of it. And I forgot that, another quotation mark in that. Look at that. What's that? What? You grade this one. Is it a 4, a 0, a 2, 3, or a 1? Right? Just read it. And based on what you know about stars, and just talk to your neighbor. See if your neighbor agrees. What's that? Oh, students, on this one you have to type in a letter and then hit the send button. And then you'll get a check, because this one is set for short answer. Nice. All right, look at this. All right, now can you click? Good. I want all of them.
Oh.
Can you go down? No, I don't want those. Those are incorrect answers. I want a letter. I don't want a number of 3. Somebody typed it. I don't get this. Well, that must be why it wasn't working the other day, because we have to go down here.
What is happening?
I don't really know. This is definitely strange looking.
They must
All right, 20 seconds. We're going to show them this one. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, we're going to show you this one. And
Or not.
what is going on? See if you can move it over to the... Oh boy, we can't show you. It does not seem to be cooperating here. Somebody's been messing around with these computers in here. This room gets a lot of abuse. All right, I'll read it off to you. Those that voted for A, 6%. Those who voted for B, 14%. Those who voted for C, 28%. Those who voted for D, 22%. And those who voted for E, 28%. All right, so the biggest group is C and E, 2 points and 4 points. But nobody had the majority. But of course, this is the answer. That's a 4-pointer. And here's one way to look at it. This graph, it's the flux. It gives you the height of the graph, the vertical component, or the vertical axis, shows you the number of watts per square meter. All right, so everything for Procyon A is above the sun. So no matter what wavelength you look at, watts per square meter is higher, therefore the temperature is higher. You can just, all right, so it's a short answer, but it's a good one. All right? Now, I want to take a break and hand back exam printouts, and we've got them right here. So let me pause the podcast, and let's... Okay. Let's continue, and let me just make a couple announcements concerning the printouts that you just got. I know a few of you guys got up here a little bit slow, and to get through the whole list of students, we just got to go through it one at a time. If you're not up here fast enough, we'll catch you at the end of class. If we dismiss a few minutes early, it shouldn't be a problem. All right. Now, remember, your exam printout is just your Scantron points. All right. You also have some clicking points. And your Scantron score is in web courses, but I haven't activated it. I'll do that after class. Your clicking points have been up since last night. Hopefully you saw those. All right. And I think we've got all of them posted. So... and for those of you that came late, we're going to have office hours tomorrow, special office hours tomorrow, Friday, 9:30 to 11. And Talia, they're going to be in my office, room 156, in the Physical Sciences building. So if you can squeeze it into your schedule, slide over and we can talk about grades or whatever needs to be talked about. All right? Before we depart from the topic of exam 4, let me just ask you to take a look at your printout, okay? and double check it for double answers, because those will be marked wrong, and double check it for blanks, because a blank will be marked wrong. And if you have it, raise your hand if you have a blank or a double. Anybody? Okay. Usually one or two people. Okay, double check it. And if you have, bring them on up right now and we'll get them squared away. Bring your Scantron printout up. If you have a blank or, yeah. What's that? Yeah, if you have two answers on the student column, that's a double. And usually, what do you got here? Yeah, all right. We'll try to get square. We'll just look at your Scantron. We'll dig it out of the pile. Okay. And matter of fact, could you do that for me?
What do you need?
Yeah, the Scantrons. We don't have the Scantrons, I guess. Is that right?
Yeah, you gave them the stand on to give you the printout.
The Scantrons must be back at my office, so I'll have to look at these later. Okay, just put them on the. Oh, actually, let me put them in my pocket. That way I won't forget it. Okay, you guys have just brought these your Scantron printouts. I'll get them sorted. I'll look at your Scantron, dig it out of the pile. It's a big pile, so it's kind of a pain in the neck, but we'll get it. Okay, let's keep going. I want to talk about the end state of stars on the main sequence. Now, we've talked about main sequence. We're going to continue using the main sequence as a reference zone on the HR diagram. And we're going to be talking about HR diagram today. And we've mentioned already that the physical state that encodes on an HR diagram as the main sequence is hydrogen fusion in the core of a self-gravitating blob of hydrogen. In other words, a star. If it's burning helium, if it's fusing helium, it's not going to be on the main sequence. It's going to be evolving towards its end state, and that's what we're going to talk about today. Now, here's a diagram. I want you to make a note. This is chapter 22 now we're talking about. This is figure 4. It's about a cluster called M41. And M41, it uses the letter M. That's a designation. Because the guy that first located it in the sky with his telescope was a French guy named Messier, Messier. And his catalog, the Messier catalog, this is number 41. The Andromeda galaxy is M31. And there's other galaxies and nebulas and stuff. And this one's a cluster of stars, M41. Now, if you look at this carefully, here's the HR diagram. Let me get my cursor over here. Here's the HR diagram. Here's the main sequence, the theoretical main sequence is that red line. Now, we have guys that, they can simulate hydrogen fusion, mass of the sun, mass of 20 suns, mass of a tenth of a sun, and, work it out. And we know where it's going to be on the HR diagram. That's what this red line is. And most stars will be, close to that, a little above, maybe a little below. But they'll be close to that theoretical line, except for right about there. Now look at that. Don't look at each other. Look at this. Come on, in the back. Don't look at her. Look at this. Yeah, good. Look at that arrow. And it's a visual decision you have to be able to make. You're looking for the main sequence turnoff. Go ahead and write that phrase down. The main sequence turnoff. The stars, they're not going to last forever on the main sequence. Eventually, their core is going to have all the or a majority of the hydrogen fused into helium, and then new stuff starts to happen. They become a red giant star. Now that's what we got up here. These few dots up there, there's not many of them. And this one kind of, see this one right here where my cursor is? He's kind of out there by himself. But, when we're looking at a star, we're looking at them as they gradually move across from the main sequence over to the red giant branch. So it's kind of a snapshot in time, really. But in a million years or so, it might be all the way over here in this other clump. But at any rate, these guys have moved off the main sequence. And this point down here is where the star, that's what we call the main sequence turnoff. Now, why is that important? Well, as I mentioned, our theoretical models, we can figure out, make a model of a star with 10 solar masses or 20 solar masses, and we run our model, and we can figure out that the lifetime, so this is one up here, it's about 20 solar masses up there. The lifetime is going to be about 10 million years. So draw yourself a little kind of easy HR diagram. All right, and this one's coded with luminosity on the powers of 10, and then it's got colors and temperatures on the bottom. And notice how the temperatures don't decrease uniformly. All right, the colors look like they're decreasing uniformly, but not the temperatures. All right, and that's the horizontal scale is where the real differences are in HR diagrams. Sometimes they have a curve to them, sometimes they look more straight, and usually it's because of the horizontal scale. Anyways, so stuff up there at the blue end, up there in the O's and the B's, is going to be heavier, and a lifetime, the theoretical astrophysicists, of which I am one, will calculate that, okay, something that big, 10 million years, tops. Then it busts out of there for the giant branch, blue giant or red giant. Right now, something down here about where the sun is, the SUN, Alex, is about 10 billion years. Okay, so in the middle of your, put a dot where the sun is in the middle, it's a G class. And sun's down there. And make a note, that's about about 10 billion years. So our star is kind of in the middle there, actually toward the low end. And then down here in the reds, you're starting to get really, really slow burning stars. They're not very heavy, maybe a tenth or less of the mass of the sun. And their lifetime is really, really long. So, these red stars, they're small. The gravity's not that intense, but it is intense enough to get a little bit of a nuclear reaction core, fusing hydrogen in the core, but not as big as, these ones up here, you got buku hydrogen fusion in the core, and that's why they live so short. They got more hydrogen, and they're burning it faster. Okay, now this one doesn't have much hydrogen down here, but it's burning real slow. It's fusing really slowly. So this whole idea, we can actually leverage that to figure out. Oops, I'm going the wrong way. Sorry. Here we go again. All right. We can figure out the age of a cluster like M41. All right, because what we do is we look at the main sequence turnoff, and that's good. There's stars that are old enough theoretically to start motating over to the red giant stage. All right, and our theoretical predictions tell us, okay, that one's going to be about 100 million years, or that one's going to be about 10 billion years, or whatever it is, wherever it is on the main sequence, we can figure out how long it's going to lay there in the main sequence before it cuts off. Now, here's an example. Distant star cluster like M55. Now, this one's a globular cluster, and it's another Messier object, number 55. in his list. And it is actually kind of an interesting object. It's in our galactic halo. And what that means is it's not in the disk. It's not orbiting the nucleus of the Milky Way galaxy, you know, down there where that big black hole is. We're orbiting in the disk. And most of the stars in the Milky Way are in the disk. But there's globular clusters that in the early formation of the galaxy form clusters, and they're still on, you know, orbiting on some kind of a slanty orbit around the center. And so they're easy to see, you know, because they're up there above the disk or down below the disk. And so we can actually see them and count them. They're gravitationally bound. There's enough stars in there that they keep together as a globular cluster. All right. Now they can be obliterated by another globular cluster. You know, if they collide or interact, they'll be pulled apart. But you know, if they just keep on their own, they're just going to orbit, 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 orbit. And the good thing is they're all about the same distance. They're pretty far away. So if we get an apparent magnitude and a color, you know, we can make an HR diagram because we know even if it's an apparent magnitude, if they're all about the same distance, yeah, we can handle that. That's like having a bunch of different light bulbs, but all of them over at the Ed building. Yeah, we can handle that. We can figure out their brightnesses from that. Now this one's got about 100,000 stars, and we're going to do the HR diagram of it in just a second. And the other way to think about it, you know, I've given you this vocabulary term, the Mainsequence Turnoff or the Mainsequence Cutoff. The other way to think of it is ask yourself, what's missing from the HR diagram, or what's missing from the main sequence? And that's this last one. The age can be estimated by what's missing. It's old enough to turn off, to move over to the red giant stage. All right? So emphasize that word. What is missing? That's another way to think of the main sequence turnoff. Here's what the M55 HR diagram looks like. Question? Repeat? What causes it is the fusion of higher elements than hydrogen. You know, all the stars on the main sequence are fusing hydrogen in the core. But then eventually they're going to fuse enough hydrogen into helium that now all the dynamics change. The core contracts, gets hotter again, expands the star into a red giant, and starts fusing helium. And that's how it goes off to the red giant branch. And you can see that here. Look at that. This is a lot of dots for M55. And here's the main sequence turnoff right here. And we've got some blue giants up here. And we've got a trail of... No, but here's the turnoff. All right, so the theory is, how old do you have to be, theoretically, on the main sequence for your yellowish stars here, B minus V of about 0.4, to be your turnoff? In other words, the stuff down here in the reds in globular cluster M55, that stuff's going to cook till the cows come home, baby. 100 billion years. All right? That's hardly ever, you know, nobody's going to be around when that stuff turns off the main sequence. All right? And the stuff up here in the blue end, long time ago. Long time passing. You know, the blue stuff up there, 10 million years, bang, giant stars everywhere. But now, somewhere down here, and the sun's probably around it here. So this one, yeah, about 12.5 billion years is what they figure for the globular cluster M55. All right? So what's missing from the main sequence of M55 is everything that has a main sequence lifetime of 12.5 billion years. So all the heavy ones, and all the slightly heavy ones, and then the medium heavy ones, and even the sun. You know, sun's just kind of an average, you know, it's a smaller star. It's not like, you know, a Spica or anything like that, but, you know, even the sun would be off here. All right, because the sun's lifetime, well, you know what the sun's lifetime is, 10 billion years. All right, and here's just to review. There's the theoretical curve for the HR diagram, and a few time stamps up in the blues, down around the sun, then down in the reds, 100 billion years. That stuff is still cooking. Everything else is missing. There's M55. Okay, here's the HR diagram for M55, a subset of all the stars in our galaxy. And you can therefore say that the age of M55 is about 12.5 billion years. All right? And that is how we leverage the main sequence turnoff for a cluster of stars to get the age. And we're pretty confident about this. Now, I'm going to give you a famous situation that arose about 20 years ago. The age of these globular clusters, you don't really have, all you have to know is the main sequence. And find the main sequence, theoretically, find the turnoff, 12.5 billion years, no problem. The problem arises when you compare this to other ages that we can compute. Now, the universe, for the past 80 years, for the past 90 years now, we know that the universe is expanding. All the galaxies are redshifted. For instance, all the H alpha lines for all the galaxies that we see, except for the Andromeda galaxy, excuse me, I just burped into the, gosh. All the galaxies that we see, except for a few close to us, like Andromeda, the H alpha is redshifted. And the helium lines are redshifted. Every spectral line is redshifted. And what that means is all the galaxies are moving away from us. And the further away, the more redshift, the faster they're moving away from us. Now, Einstein and a bunch of guys back in the 1920s figured out, okay, what that means is the universe is expanding, and therefore, what a bunch of guys in the 1930s figured out, okay, if that's really true, if the universe is expanding, at some point in the past, it was all clumped together in one big, hot, dense, compact object. And that object they call the Big Bang. All right, now the theory of the Big Bang is that it leaves behind, after about 100,000 years or so after the Big Bang, it leaves behind a remnant of all the light produced by all the hydrogen and electrons in the universe, that once the universe expanded far enough, all that light was free to stream wherever it wanted in the universe. All right? So the universe contains this light from a few 100,000 years after the Big Bang, because the Big Bang, it got so big, it got less and less strong gravity and cooled off to the point where it was about the temperature of the sun, actually. The entire universe was about the temperature of the sun. And when that temperature hit, then all the light that was mixed in with all the matter was able to stream freely out anywhere in the universe. Now that light, the universe we think is contained. And so we think of all that light, all those photons of energy, as a gas. And all gases cool as they expand. And the universe is expanding to this day. And so that photon gas has cooled. And now, instead of being the temperature of the SUN when it first formed, very soon after the Big Bang, now it is down in the infrared and microwave region. It's way down. It's cooled off to that degree, right? The temperature is actually a few Kelvin instead of 5,800 Kelvin, right? We can still measure it. We've been able to measure it since the 1960s. Now that radiation, we see it in all directions, no matter where we look, in the sky. If we look, everywhere in the sky at a certain frequency, and that radiation, it's called, I'll give you the vocabulary term, cosmic microwave background, CMB, cosmic microwave background. It's a microwave signal that, they first found it, down at Bell Labs. They were designing these microwave antennas, to carry telephone calls in the microwave frequency. They still use them. And they were calibrating them, and they got this one signal. They couldn't get rid of this noise. It was, excess noise at this certain temperature, and what is this stuff? And they figured it out. It's the remnant of the Big Bang, the CMB, the cosmic microwave background radiation. We're still studying it today. Now here's the kicker. In the 70s and 80s, their measurements of the cosmic microwave background indicated that the temperature of it indicated that the universe was about 10 billion years old. All right, so write that down. Early studies of the cosmic microwave background indicated that the age of the universe was about 10 billion years. It cooled down enough. So they looked at it, they looked at the peak wavelength, and they said, all right, from what we can tell, this has been cooling down for about 10 billion years. All right, very nice. That has nothing to do with HR diagrams. So it's independent of what the globular cluster, M55, and other globular clusters told us. So the problem is, 20 years ago and more, we've got globular clusters that are older than the universe. What? So make a note. About 20 years ago, the conflict or the controversy was that we had globular clusters that, as far as we knew, we were confident about the globular cluster age, that it was older than the universe. And I'll never forget, I was at a black hole conference in Canada, and Stephen Hawking was there, and all kinds of big shots. And, I was a grad student. My advisor was there, and, he wasn't even a big shot. But all kinds of big shots up there giving talks about black holes and stuff. And a few years prior to that, they had lofted a satellite called COBE, Cosmic Background Explorer, COBE. And COBE's mission was to measure as precisely as possible the microwave background radiation. Do it again, from space, not from Earth, but from space. And I'll never forget, we were up in the mountains of the Rockies, not British Columbia, but up in Banff at this conference, fancy conference center, and all kinds of big shots, Black Holes Conference. And one afternoon, the news broke on the internets that COBE had measured the microwave background, and their calculation showed that the universe was like 13 point something billion years ago, 13.7 billion years old. And so, I'm at this conference, and my dad came out to visit me from New Jersey, because he wanted to see Stephen Hawking as well. So my dad's out there, and this news broke, and it was just like, I'd like to say it caused a ruckus, but these guys are eggheads, but it turned into a beehive. It was literally very interesting to see. Everybody was, oh man, this is great. Because now, with the new Kobe measurements, we now had this problem licked. All right, 12.5 billion years for M55, no problem, because the universe is older than that. Ding! We're squared away. All right? No antagonism now. And we've been measuring, we've got big satellites up there now, mapping out the microwave background to this day. And so, but that was kind of thrilling, It happened when I was there. So I could see all these guys huddling. What does it mean? So here's a pull quote from chapter 22, section 3, checking out the theory. And this is basically your logic for the main sequence turnoff. What is it? How do you work it? Well, it means that no stars are left near the top of the main sequence, depending on the age of the cluster. Only the low mass stars near the bottom remain, so the little red ones. All right? The older the cluster, the lower the point on the main sequence where the stars begin to move toward the red region. All right, so if you had a cluster that was fairly new, it might be, if it was really new, it'd still be up there in the blues, in the O's and the B's, and before you see the turnoff. Okay? But M55, it's down to 12.5 billion year part of the main sequence. So that's the theory behind the main sequence turnoff, and it's a pretty important use of the main sequence in the HR diagram. Now, what I want to do now is, just for a few minutes, talk to you about what happens during the retirement of stars. In other words, what happens to stars when they move off the main sequence? And then there's a couple different categories of stars, and it's determined by the mass. Smaller stars will leave the main sequence and expand to giant star status. Because they're fusing helium now, and that changes the dynamics. It's hotter at the core. Okay, so it could push the outer envelope of the star to a higher altitude, therefore cooling it, making it big and red. Okay, so you get these red giant stars. And in the process, they blow off, they'll have temporary instabilities, in other words, like a shock in their dynamics, a rapid change, and a lot of times it'll blow off an outer layer. Now, that's what you're looking at here in this image. Down here in the center, let me move my cursor. See this little star there in the center? Yeah, that star is what remains after it's blown off a lot of its outer layers. All right? Now, we call those things planetary nebula. And if you want to do some searches in Google and look at some really awesome photos, just type in planetary nebula. Now, they're not planets. I don't know, some guy decided to use the word planetary because maybe they thought they were planets, but now we know that they're not. They're just rings or spheres of gas and dust blown off, kind of like the solar wind. The solar wind is very gently blowing, even coronal mass ejections, much more gentle evacuation or blowing off the surface of the SUN. And the sun doesn't look like this, but eventually the sun will. It'll blow off a few outer layers and it might look like this. Now, the leftovers after you blow all those layers is a white dwarf. And that's what you see in the center. It's usually pretty hot in the ultraviolet. And the white dwarf is going to be about the size of the Earth, plus or minus a few thousand kilometers. So it's on the order of the Earth in size. And the white dwarf is no longer fusing. A white dwarf has stopped fusing. Still pretty hot though. So it's got a lot of radiation to zap out into space and cools down that way, but it's not fusing. So here's the white dwarf here that I mentioned. This is NGC 6369. NGC stands for New Galactic Catalog, I believe. Yeah. Repeat? Yeah, that's like the sun will possibly look a little bit like this. The sun will become a white dwarf, we think, 5 billion years from now. And it'll blow some of its outer layers, and it might look a little bit like this. All right, so here's the outer layers. All right. And it just blows them off, and it's just kind of like puffing them off. Not too violent. The question is, does the sun ever completely burn out? No, it's not gonna nuke out all of its core down to zero. Can't do that. And we're going to talk about that, and you're going to study about that over the weekend. Here's another one. It's kind of a bubbly. And you see the star in the middle of that. Here's the Ring Nebula. A lot of you guys saw that at the observatory. Here's a close-up. You can see the white dwarf in the middle of that. Here's another one. I mean, you just type in Planetary Nebula, you see zillions of these babies. And this one's kind of cool because you can see kind of an axis at 45 degrees tilt. And down here in the middle, that's your white dwarf down there. Now, let me ask you another clicker question. And this is really the question that determines where you go for retirement. Are you going to move to Florida and become a white dwarf star? Or are you going to move to San Diego and become a giant and go into a supernova? Right? Multiple choice, yeah. So go ahead and answer this question. 30 seconds to vote. I just touch screened it.
Noise.
I don't know what was going on with that. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. 0.
Oh, yep. Back.
Thank you, Courtney. Yeah, low mass star. We're not done yet. We're still... Now, we're going to dismiss in just a minute, but let me just point out to you what is ahead. We're going to look on Tuesday at the trouble with iron 26, iron 56 we call it. And iron 56 is involved with supernova explosions. Now, you're going to have a reading assignment this weekend concerning iron 56 and supernovas. Be alert. I'll try to get it up by lunchtime tomorrow. Okay, you're dismissed. Come on down and get your printouts if you still want it. 0. See, because you forgot the bonus pencil.
Oh, dang it.
See, that's why you got to put napping on that.